Right. Okay, so this is a project I've worked on with Tomo Matsumura, who's at IPMU in Tokyo, and Guillaume, who's at APC in Paris. And I'm a PhD student in between the University of Oxford and Cavali IPMU. Right, so my work in general is mainly related to CMB polarization experiments. In this context, as we all know, instrument observe the maps of the sky through a series of systematics, both from the sky in the form of foregrounds and from the instrument. And this signal is then received at the detector in the form of time-ordered data, from which we reconstruct clean maps of the sky that we can analyze to extract polarized CMB signal and then extrapolate the cosmological information from this. And given the presence of these systematics, it's difficult to detect the low amplitude, large scale CMB modes. And so, especially given the increased sensitivity of the new generation of CMB experiments. And so my work during my PhD has been focusing on the implementation of some foreground cleaning techniques and how to mitigate some of these instrumental systematics, in particular related to the half-wave plate, which is what I'm going to talk about here. Right, so as a general introduction to half-wave plate, so a question would be, why is a half-wave plate then important in polarized CMB experiments? And to have a general idea. So if we take the input sky signal described by the Stokes parameters, a continuously rotating half-wave plate that modulates an impopolarized sky signal onto a detector with output given by the expression here for D in time, which is called time-ordered data, where the polarized sky signal is then modulated by a modulation function here in the exponential, and theta is the half-wave plate rotation angle. So the phase of the half-wave plate then is related to the frequency of the half-wave plate this way, and to the spin rate of the half-wave plate multiplied by time. So essentially the rotating half-wave plate has then a steady velocity given by the frequency of the half-wave plate, such that the phase is given by this expression. And the modulation frequency is then given by 4 times the frequency of the half-wave plate. And so the detector outputs is then modulated at 4 times this half-wave plate rotation frequency. And if we Fourier transform the equation for the time-ordered data, so written in time domain, and we go into Fourier domain, then we can have some intuition of what is actually happening. So if we have a single Fourier mode sky signal composed by the Stokes parameters, and then we plug that into the equation for the TOD, and then Fourier transform this, then we see the polarized sky signal, so Q and U, are moved from a frequency omega of the signal to frequencies 4 times the omega of the half-wave plate plus the omega of the signal. And this is why the intensity sky signal is left at the omega of the signal, which is then the signature of amplitude modulation. And so what we see is then that the sky signal now for polarization appear at frequencies plus minus omega of the signal around the carrier frequency for omega of the half-wave plate here. And so in other words, this polarized signal is now in a wide noise dominated frequency regime. And so we use a frequency of the half-wave plate that is large enough such that the polarized sky signals are up-converted to frequencies above the 1/f noise. And so this is one of the main reasons why we use half-wave plate. So to deal with this 1/f noise, so large long time scales effects, and also to mitigate some differential systematic uncertainties like the ones related to beams and band passes. Right, then so we work with TODs to model some of the instrument systematics, such as the half-wave plate induced systematics. And more specifically, we can see that the TOD is then a linear function of the sky signal and the noise. And so we model the TOD for a single detector as a linear combination of the signal and the noise. And for the signal part, we simulate the set of the Stokes parameters, and then the scattering pattern and the telescope response goes into a binary pointing matrix P, which projects then in time domain the 3 Stokes parameters. And then the noise is Gaussian. But when we actually look at realistic time domain data, there is a lot of sky and instrument systematics that we have to deal with. And working in TOD is why it's useful to introduce and characterize these instrument systematics, such as the ones from the half-wave plate. So the way to model these instrument systematics, what is used generally is the Mueller formalism. So in general, the incoming and output light is described by the Stokes vector, and the optical components of a system can be described with Mueller matrices, which describe then how the Stokes parameter transform. And for an instrument with several components, the Mueller matrix is just the product of the Mueller matrices for each component. And then IQ, U, and V are just the standard Stokes parameters after the half-wave plate. And the matrix M opt is the Mueller matrix of the light transferring the optical system, and the matrix MH is the Mueller matrix of the half-wave plate here. So as we saw, the half-wave plate is then used to modulate the polarization, and in the ideal case, the input polarization is then flipped with respect to the half-wave plate extraordinary axis. And so in terms of the Stokes parameters, you see that we've got so this operation is equivalent to inverting the plus U polarization component to minus U, and then plus V to minus V. And so the Mueller matrix of a perfect half-wave plate reduces to the identity matrix. But of course, in a more realistic scenario, however, the half-wave plate introduces by itself a new series of systematics. And so some of these terms will become non-zero. Also for this kind of study, to simplify things, we consider any other optical elements other than the half-wave plate to be described by their ideal identity matrix. And we also assume no input V term, since the half-wave plate is usually the first element in the optical system. Right. So if we then consider a measured polarized signal, that is the true sky signal as in, modified by a systematic effects, then in general, we can define a vector delta S that defines the uncertainties in the Stokes parameters in terms of the Mueller matrix for a given systematic error defined by these delta MCs. And delta S here is just the vector of the measured Stokes parameters minus the vector of the Stokes parameters coming from the sky. So for a realistic half-wave plate, then the different systematics will affect different terms of this Mueller matrix. And the systematics are related to different half-wave plate properties here. So in this study, I'm mainly considering the systematics of the halfway plate that affect the polarization efficiency and polarization rotation. And then we can also use this study, which is something that we're doing, so it's currently ongoing, to obtain then gain and thermal stability requirements as well from the point of view of coupling with HWP leakage due to the half-wave plate non-idealities of rotation. And so we can then expand this study, and that's one of our aims, to see where the coupling of systematics will become important. Right, so in this study here, then we're studying the rotational instabilities of the half-wave plate. And in particular, so the half-wave plate angle is determined usually using an optical encoder. And so by studying the half-wave plate angle instabilities, we can determine then calibration requirements. So we want to know essentially how well does an encoder needs to measure the angles, not to bias then the cosmology. And in practice, the miscalibration of the angle is then a major source of systematic errors, which gives a leakage of E modes to B modes and B modes to E modes as well. But of course, given the amplitude of B modes, that's less relevant. And so this biases the estimation of the tensor to scalar ratio. And so if we do the calculation, let's say with a bit of calculation, a bit of magic there, we can find that essentially the Mueller matrix parameters, such as those associated with polarization and efficiency, so the blocks, the amplitude of the block QU of the Mueller matrix in particular, are the one relevant for the effects of the instabilities of the half-wave plate angle. And in power spectrum, we see that these systematics have the effect of reducing the polarization map by a global factor and introduce a need to be leakage at the power spectrum level here, which is visible analytically. And so we use this sort of rho term to characterize the polarization rotation, and then this epsilon term for the reduction of efficiency of polarization. Okay, then here we've seen, right, how to go from sky to time order data. Then to go from the time order data to the sky, we use Mapmaking. And so with our data model in hand, we can then reconstruct a map of the sky where in general, we assume a simple Gaussian likelihood for the data, such that from the likelihood of a sky M, given the data stream, we can recover a linear system as the maximum likelihood estimator, where M is then unbiased and Gaussian distributed with a covariance given by these matrices. And the general idea is just that we need to invert this matrix, and usually we use chi-square minimization to do that in order to recover then the Stokes parameters of the map in each pixel. But this is not actually so trivial to implement when the number of samples in the TODs are large and in the presence of noise. So given that the matrices involved are too large to solve by direct inversion, we avoid maximum likelihood map making here, and we use a faster method. So we solve the linear system iteratively by means of a conjugate gradient method to invert this equation without ever explicitly building this matrix. So in other words, this matrix can be seen as an operator, and so we can avoid constructing it explicitly. And we've got that P then projects the pixel values into time-ordered samples, and the inverse noise performs inverse bias weighting of the data, and then the transpose of P projects the data back onto the map. And so since these techniques are iterative, we need to run several iterations to arrive at an acceptable estimate for our map. And the number also of required iterations strongly depends on the noise model on which and on which maximum scale we aim to recover the map. Okay, so in general, the framework that we use to analyze then these systematics that we've built, we have this framework that goes from the observed maps to the TOD, and then from your TOD to your clean maps, and finally to the cosmological parameters. So in this case, the tensor to scalar ratio. And to study these effects, we use the following simulation. So we start with the simplest case, where we include only one detector and CMB only maps to evaluate the actual effect from the half-wave plate. And then we are in the process of adding foregrounds and having realistic then results for that. So we start with the ideal case, which means that there is no systematic included in our simulation. So the phase is then the same between the data simulator and the map maker. So the input maps are the input maps to the TOD simulator, and then the output maps are the ones that come from the map maker. And then the residual between the input and output maps of the map maker are set by the conjugate gradient efficiency through the iterations. And so we find then the lowest possible residuals in power spectrum space. And we test that actually our framework works. Then we start introducing the systematics at the phase level. And so we start by introducing a constant phase offset over time. So we introduce this phase lag intentionally. And so I have a single delta of the phase fixed throughout my simulated mission. And here I'm just plotting the phase over time. Right, the phase is just going up because this is the actual half-wave plate position. So the phase is a function of time. And the slope here is just the rotation rate of the half-wave plate. And in this way, then we include this polarization systematic rotation, and we see with our model if what we get is actually what we can analytically predict. Right, and so in this case, we see that the polarization rotation effect that we have in our model is the dominating effect. And you can see that from the left plot where we've got the power spectra for the input and output of the Mapmaker. And we also see then the same effect, so that we expect this polarization pattern rotation in the maps, and we see that from the input and output maps. Here I'm plotting just the polarization ones. So right, on the left, as I said, there are just the TT, EE, and BB spectra calculated from the input and output maps and from the residuals. And we see this E to B leakage. So for example, the BB output spectrum in orange sort of resembles in shape the EE spectrum in blue and shifts away from the input BB in red. In our power spectrum model here, the second term becomes dominant. And in the figure on the right here, I'm plotting the BB spectra where we use the model to fit for the angle, and we recover the input angle of the simulation. So we see that our model is actually valid to see this effect for our constant angle. Okay, then we start introducing more realistic variation of this half-wave plate angle. And we start with a random delta of the phase. So we draw random samples from a normal Gaussian distribution, where P here is just the standard probability density for the Gaussian distribution. And mu is the mean and sigma is the standard deviation. And from these, if we start increasing then the sigma, we can set some constraint on what the maximum sigma you are allowed to have per bolometer sample. And you can get a resulting constraint, so a requirement on the sigma. And the accuracy requirement that we want here is we set essentially for each systematic that one is studying, we can say that we want that to be 1% of the total experiment sensitivity on R. And so given the new experiments for CMB, we want delta R to be at the level of 10 to the minus 3. And so we set the systematics to be to the level of 10 to the minus 4. Here again, I'm just plotting the phase over a short time just to show the variation and calculating the phase and offset for different standard deviations. And the time is in sampling time, so given a sampling frequency of 19 Hertz. And the idea here is that you can already kind of see that since the phase here is going to be a random number, you expect that after stacking them over time, then the uncertainty will average over sky. And this is what we see in our results. So we see that the EB mixing effect here mainly cancels out. And you see that the dominating effect is the scaling of the amplitudes of the EE and BB power spectra, which means that we are reducing the polarization maps by a global factor. And so I expect my epsilon term in my parameterization to come into play. Okay, and so if we want to know also how bad of a sigma we can tolerate, we can already use the information that we get from the spectra. And here I'm plotting the case of sigma equal to 0.1 radians, which is equivalent to approximately 5.6 degrees. And we see that in this case, the residual BB is 2 magnitude lower than the lensing BB. So in this way, it's actually already good in a way that it is 1% of the lensing power spectrum. And so we see that in this case, the result is for a sigma, the result for a sigma of 0.1 radians. If we convert that into the angle, so we divide by 4, it means that we find that the angle rotation, as long as it is random, can be as large as this 5.6 degrees divided by 4. So we have an idea of what to expect. And we expect that then the angle that can be tolerated, the sigma in our instrument, will be approximately 1.4 degrees. But this is only true if the sigma is a pure random. And so this might not be the best physical model. But this model, however, allows us to explore a sort of half-wave plate instability model where we are dominated by the measurement error. And so the sigma that we find corresponds to the precision that is needed for the encoder to achieve a given delta R. And we see with different, we've tested this with different increasing values of the sigma. And here I've got the TT, EE, and BB spectra for the different values of the sigma. And these are the output spectra, and the input is in black. And then I've got the residual spectra on the right. And we see that as the sigma increases, then the output CL start to deviate from the input. So the residual CLBB in particular increases as the sigma increases, as we expect. And this corresponds to a net depolarization effect in our maps. So here I evaluate the absolute bias on R calculated from the residual maps. And so we get what essentially is the level of precision of the encoder measurements for the halfway plate to avoid biasing the cosmology. And so at sigma phi equals 0, the fit gives essentially no B-mode signal, so with no systematics. And then as you increase the sigma, so the variation of the angle going to the right on the x-axis, then R gets more biased. And so the more the angle is varying, the more you're averaging the angle. And so effectively what you have is this depolarization effect, and the effective R is then going to decrease. And we can estimate that values of sigma of the angle that are greater than 1.4 degrees, as we expected from what I was saying before from the spectra, is going to bias our results for R. Right, then eventually we get to a more realistic half-wave plate rotation model, where we take the delta of the phase to be sampled from a Gaussian with 0 mean and variance given by the power spectrum 1 over f squared, which is represented here. So the idea is just that the half-wave plate drifts by accumulating errors in between two measurements. And so we use this 1 over f squared spectrum. And as you increase time and you recalibrate, so you relocate your angle by remeasuring the position with the encoder. But then in between the two measurements, the angle is actually drifting. So for the drift, we use this then random walk essentially, so an intuitive behavior of 1 over f squared. And we put a limit at the low frequency, so what we call fni, which is the frequency corresponding to the inverse of the separation time between two measurements made by the encoder. So if frequency is lower than fni, you expect to be limited by only the white noise, because that's when you are measuring your half-wave plate location. And in the different measurements, you assume that you lock your half-wave plate, so you determine the angle with some error regularly. And so we avoid having the half-wave plate drifting completely because we are recalibrating every time with the encoder. And so we parameterize this spectrum with two parameters, the sigma of the TOD, which is of the TOD of the angle variation, and the knee frequency of the spectrum. So we see again on the power spectra the effect where I fix the value of the sigma TOD and I vary the knee frequency. And the same as before, we see that we have an effect on the auto power spectra and not on the cross power spectra, so only on BB and EE. And we see that as we increase the knee frequency, or actually if we decrease the knee frequency, then the effect is getting bigger. And we get that from the constraints on R as well, where higher FK for higher knee frequencies than for a given TOD gives a higher bias on the delta R. And delta R is also not varying much, only between small values. So this means that it doesn't depend a lot on the sigma. And lower knee frequencies correspond to less perturbations. So it's difficult to predict the behavior with the fixed sigma TOD. Right, so for a given amplitude of the white noise, so the sigma value is fixed. If you lower the FK, then you should remove more high frequency perturbations, and then your bias should be lower. And so we ran a few simulations, but then to optimize the space on the disk that was used to save all the results for the simulation. So we've got a sparse resolution in this 2D graph for R. Then we are a bit more analytical on these, and so for a given we fix a given FK, and then for different values of sigma K, of sigma TOD, sorry, then we predict what R is going to be, and we see that again for the different values of the knee frequencies, we find that a sigma TOD of 0.08 radians per sample, and greater than that is going to bias our results for the cosmology. So this is where we're at with this study now. We are implementing more things in our framework. In particular, we are including foregrounds, and then we're doing coupling of more systematics. And we are starting to put down a paper on this study and a public repository for this. So yeah, if you have any questions, let me know, or stay tuned for the updates that are coming. Thank you.